Certainly the most difficult of all of the stresses to understand conceptually is the stress associated with temperature, because it's not just a matter of sitting there and looking directly at the system and seeing obviously what's going on. But I'm going to show you some tricks that will make it easier for us. But just to understand what we're going to be doing, we're going to be applying temperature stresses. Our temperature stress can be either to heat the system up externally, or it can be to cool the system down externally. And if you want to remember why it is that the stress is so vital and how it is that we know that it is going to have an impact, remember that there is a temperature dependence to the chemical equilibria that we see, in the same way that there's a temperature dependence to thermodynamics. When you look at the thermodynamic equations, you see temperature values littered throughout it, impacting what the value of delta G is. Well, the same thing's going to happen here. By changing the temperature, increasing it or decreasing it, I'm going to be able to change the K values I see. And in just a moment, I'm going to show you how this is actually calculated quantitatively with the Van 't Hoff expression. Here, my only interest is talking to you about whether or not a reaction shifts left or right according to LeChateliers in response to temperature changes. So I'm going to write down a couple of chemical reactions here, and you can see what basically is possible. Remember, reactions can be either exothermic or endothermic processes, and by that I mean they can either give off heat or they can absorb heat. So if I show you a chemical reaction in which A goes to form B, that reaction can either give off heat or it can absorb heat. And I like to write the reactions like this when I'm teaching you about LeChateliers Principle, because then suddenly heat becomes one of the components in the system. Now, I might say to you, so that you know that this gives off heat, A goes to make B and heat is released, and so you'll put the heat on the right side. Or I may tell you that delta H is negative and you'll put it on this side. Or I might actually write it this way. Or I might write it this way by saying heat is put into the system. Or I might tell you that it's an endothermic process. Or I might tell you that delta H is a positive number. Either way, when you set up LeChateliers Principle problems to work them, it's always important to write down, until you get used to it, that the heat is on the left or the heat is on the right, and then you can solve. All right, so now let's go ahead and solve these systems. It's actually pretty easy and straight ahead to do when we can write these things down. I'm going to decide in this top system right here that I'm going to heat it up with a blowtorch. So I heat the system up with a blowtorch, and the system says, gee, it's getting hot. I don't like heat. What way should I shift? And the answer is it shifts to the left. By shifting to the left, it's going to make more A, less B, and K changes. When K changes, as a result, I end up having K get smaller because the reaction is shifted to the left. I've got less B and I've got more A. Suppose I cool this system down. I pour liquid nitrogen on it. The system says, wow, that is cold. I don't like that. I'm going to shift to the right away from it to get hotter. And when that happens, I make more B than A, and as a consequence, K gets larger. Let's look at the endothermic cases. I decide to heat this system up. When I heat this system up, the system says I don't like the heat, so it shifts to the right to get away from it. And as a consequence, I end up with more B than A, and K goes up. Or I decided to cool this system down. The system says, boy, I don't like it cold. I want to warm it up, so it shifts to the left. That makes less B and more A, and K goes up. So we have these four different cases, making either of these systems, the exothermic and the endothermic case, hotter or colder. You can try to memorize these if you'd like. Memorize the endothermic case when the temperature goes down, the endothermic case when the temperature goes up, the exothermic case when the temperature goes down, the exothermic case when the temperature goes up. I don't know why you bothered to do that, because you might get that messed up. If you write it down like this, though, if you write down your chemical reaction and you put the heat on the side that it needs to go on, then it becomes a simple matter for you to execute that LeChateliers Principle set of steps. Number one, what's the external stress? Number two, the system response, shifting left or right to avoid that stress. The only new wrinkle in all of this is that, unlike with pressure and concentration changes where K doesn't change, here with temperature changes, with the temperature stress, K equilibrium becomes a new value. So So now that we understand LeChateliers principle and temperature, I'm going to show you two pretty darn famous examples that have significant implications either in the kitchen or in the ocean. So the first one I'm going to show you is an exothermic case. This exothermic case may seem like a pretty boring reaction. It's dissolving oxygen, which is a gas, in water. All right, so here's oxygen dissolving in water. You can imagine doing this simply by, blowing oxygen through a straw down into water. It achieves the following equilibrium. Now, it turns out that there is a particular amount of oxygen in water which allows fish to live, because like fish breathe the oxygen that's in the water. And fish definitely want reactions that shift to the right, because the more oxygen, the more they breathe. They do not want reactions or processes that cause the system to shift to the left, because then they're left gasping for air. So if I told you that this is an exothermic process, you would then have to write heat on the right-hand side of this reaction. Now that you've written heat on the right-hand side of the reaction, the next question is, what's the temperature dependence of this with respect to LeChatelier? Let's decide that the temperatures cool down. It gets colder. As it gets colder, the system says, I want to get hotter. So the reaction shifts to the right, and more oxygen goes into water to make it possible for the fish to breathe. So interestingly, when water gets cold, fish have an easier time of it breathing. Now let's talk about the notion that maybe our oceans are getting warmer. Maybe climate change is having some sort of effect, and you're seeing the temperatures of the water in the oceans go up. If that's a reality in some parts of the world, then look what's happening here. This means then that the amount of dissolved oxygen in the water is going down, and that means, because it's shifting to the left, that our fish aren't going to be able to breathe. Heat is added to the system. The system says, I don't like that, I'm going to shift to the left, and then oxygen in the water goes down. And the interesting side effect of this is that as the water oxygen content goes down, you create anaerobic conditions, and then you have things like red tide result. So this is a very important impact from an environmental perspective, this notion that dissolving gases in water is typically an exothermic process. And it's one that suggests that we need colder temperatures to be able to keep this vital physical process taking place in the right direction. The next example that I'm going to show you is a little bit less important, but still one which is kind of interesting. This is the process by which salt dissolves in water. Interestingly, most people tend to think that when you're dissolving salt in water, that this is an exothermic process, that heat's going to be released. And in fact, there are lots and lots of examples where when you dissolve salt in water, a lot of heat is produced. Like when you dissolve calcium oxide in water, like when you're making concrete-like substances, water's boiling away on frying an egg, the whole thing is going on. It's very much exothermic. But it turns out that sodium chloride dissolving in water is slightly endothermic, which means I have to write heat on the left-hand side of this chemical reaction. So let's think about what happens then as I do something very practical. Decide I put salt in the water, and I decide to heat it up because I want to boil the water. We do this all the time when we're cooking. We want to boil our water. Well, if I have an endothermic process and I've added salt to water, and I heat the water up, the water says, hey, I don't like that. I don't like that extra heat. I'm going to shift to the right. But look what it's doing when it's shifting to the right. It's dissolving salt and making sodium and chloride ions. This is the phenomenon you see all the time at home, where you dump a bunch of salt into water because you're going to cook some pasta, and it's sitting there, and the salt's sitting on the bottom of this cold water. It has not dissolved, and then you put it on the stove and heat it up, and what do you know? As you heat it up, you make more and more sodium ions and chloride ions. So this is an interesting example of the fact that this endothermic process, one that's not all that common for salts, the addition of heat, the actual making the solution colder, is one which results by increasing the temperature and increasing the amount of sodium and chloride ions in solution.